Good. So, so our goal today is to prove Lefschetz formula. And last time we reduced the general case to the case of curves. So C0 will be a curve, a smooth curve. Curve over field K, which is a finite field. C will be its pullback, C0 times K bar. And we have the geometric Frobenius map. And suppose we have a Weyl sheaf, QL Weyl sheaf, which is just a QL sheaf on C, together with map from its Frobenius pullback to F. We call it also F. So Weyl sheaf, sheaf on C. As we discussed last time, a basic example of such a sheaf is just any QL sheaf lifted from C0. This is a generalization of sheaves, QL sheaves on C0, a mild generalization. And then, what we want to prove is that the sum of traces over all points, C0 points of K, which is the same as C points of K bar, fixed under the Frobenius, traces of the Frobenius over the geometric point lying over this. So it's K bar point of C fixed under the Frobenius. This map F induces an endomorphism of the stroke, so I can take the trace. And our goal is to show that this is alternated sum of the Frobenius acting on homology with compact support of C with coefficients in F. Okay? So here the sum consists of 3 terms because H3 and higher homology groups vanish for curves. Okay, so that's our goal. And so what are the tools here? So the basic tool is a result of Weyl. So this is, let's say that this is theorem, main theorem that we want to prove. And the tool that I'm going to use is another theorem of Weyl, which asserts that this is true with coefficients in a constant sheaf. Let's formulate it as follows. So let's see. Let C be a smooth projective curve over algebraically closed field. And suppose this time that we have any map, not necessarily the Frobenius. K can be a field of complex numbers, for example. Suppose I have any map from C to C. Then, so what I can do, I can take its, the number of its fixed points. Well, so I do not even, well, F can be, for example, the identity map. Then the number of fixed points is infinite, but the way I want to define it is using the intersection theory. So I consider the graph of F and the diagonal. So these are graph of F, and the diagonal are, closed subschemes of C times C. So C times C is a smooth projective surface, so I can take intersection of cycles. So that's a well-defined integer, and the claim is that this is, sum over I of traces of cohomology F upper star. I don't need compact support here because C is compact, C with constant coefficients. So QL. Okay? So that's the theorem of Weyl, and well, the way he formulated this alternated sum. Thank you very much. So the way he formulated this theorem, of course, he didn't know what this cohomology group, étale cohomology group is. So he just defined HI of C. So H. Let me make it even more precise here. So this is equal. So there are three groups in question, right? H0, and H0 is canonically QL, and there is no action of F on H0 is trivial. So this is just 1 minus this trace of F upper star acting on H1 of C with QL coefficients, plus the action on H2. And so in Weyl's formula, so H2 is one-dimensional, and we already discussed this, that the action of it's canonically identified with the group of connected components of the Picard group. So action of F on the H2 is just the degree map, degree F. So this is the Weyl formulation where he defined H1 of these coefficients in QL as using the Jacobian. So this is QL tensored with inverse limit over n of peak C A to the n. So I take the Picard group, I take torsion points, and I pass to the limit. I get a ZL module of rank 2G, and I tensor it with QL. So by functoriality, F acts on by pullback on the Picard group, and so it acts on this inverse limit. So, so this is Weyl formulation. Well, to make it sort of completely, this identification here, as well we discussed, it's not canonical. It depends on the choice of roots of primitive root of unity. So to make it completely canonical, it doesn't change the formula at all, but it makes this isomorphism canonical. I can put 1 here. So it doesn't change. So this because we work over an algebraically closed field, the difference, well, this twist by 1 does not affect really the trace. So this group is obtained from the cohomology with constant coefficients by tensoring it with QL, and F does not act on QL1. Okay? So I will not prove this theorem now. There will be some, so the proof uses the corresponding, relation between correspondences on C and endomorphisms of the Jacobian that we discussed in the first part of the course. And there will be a homework problem where the proof is split into several parts. So it will be deferred to the homework. So instead of proving this, I'm going to use it. I will show how the general case is reduced to this one, to the case of constant coefficients. And so to motivate, so this is a very, very nice kind of tricky argument in homological algebra and representation of finite groups. So to motivate what's going on, let's consider an example. And I will show you how, that's somehow already contains a key basic idea. So suppose, let's assume that let F0 be a local system on C0 that corresponds to an Artin representation. Of pi1 et al. Of C0. So what does it mean? So local systems on a normal variety are in one-to-one correspondence with continuous representations of a tal fundamental group. Continuous with respect to, the profinite topology here and L-adic topology. We look at the L-adic local systems. So we have some finite dimensional vector space V over QL. So this is a general linear group over this field. It has topology, L-adic topology. And so a local system is a continuous representation. So an Artin local system is such a representation which factors through the finite quotient. That's the definition. Finite group. Okay? So let's prove this theorem here for Weyl sheaf associated to such an Artin local system. So what does it mean that it factors the representation of the fundamental group factors through a finite quotient? It means that this F0 gets trivialized after a finite et al. Cover of C0. And we are going to use it. So, okay. So let's take C0. So we proof of theorem, Lefschetz formula for such F0, right? So in order to do this, let's consider finite et al. Cover corresponding to this group G. So G acts here. Right? So, okay, so now we have C, which is the best change. We have this map. And I can. So this is finite et al. Cover, et al. Cover corresponding to homomorphism from pi et al. Of C0 to G, right? So we are given a representation, and we assume that it factors through a finite quotient. I fix G. Then I get a finite. And then, so here I have the base change. This is base change to K bar. And this is also a finite et al. Cover, which could be, however, disconnected. Okay? So I give some names to these maps. So let's call it H0, and this is H. So now, lemma. Да, вопрос? Ну, у нас C0 это кривая над конечным полем, а C это кривая над алгебраическим замыканием. Okay, so first I want to express homology of C with coefficients in this local system, right? So F0 is a sheaf, is a local system on C0, and F is a corresponding local system on C. In terms of this representation V. So I claim that this is equal to HQ of C tilde with constant coefficients. So, so this is a vector space with an action of G, because G acts on C tilde. And I can tensor this, this representation with V and take G invariance. So the claim is that the homology of, in fact, any space with coefficients in a Artin local system can be expressed in terms of the usual homology of the cover where the local system is stable. Okay? Diagonal action, right. So G acts here, and it also acts here. And I take the diagonal action. So proof. Well, so we can compute this group, HQ of C tilde with coefficients in QL, as let's say this. So let's tensor it with V, and I claim that this is the same as HQ of C with coefficients in HVO star of QL. Well, this is a vector space, so let's tensor this with V. Let's put it inside. So this group is equal to the homology of C with coefficients in the direct image, because this functor is exact for finite morphisms. So V is just a vector space. It's non-canonically, this is isomorphic to just direct sum of few copies of this group, so I can put it inside. And so now this isomorphism here is compatible with the action of G. So G acts here, right? Why it acts here? Because it acts on C tilde by functoriality. So G tilde acts here, and it also acts here. So if I if I consider G invariance on this space, it's going to be the same as G invariance here. But now this G does not act on C, it acts only on the sheaf. And I claim that if I have a finite group acting on a QL sheaf, on a sheaf of vector spaces over a field of characteristic 0, then taking invariance commutes with homology. So this is the same as homology of C with coefficients in H rho star QL tensor with V, and here I take G invariance, right? So that is because this functor of G invariance is exact on the category of QL vector spaces with action of G. G is a finite group by Maschke theorem. So how to prove this? Well, you can think of G invariance as image of idempotent. So you can look at the group algebra. There is an idempotent, namely 1 over the order of G times the sum of all elements of G, and we are taking the image of the idempotent. That's a direct summand here, right? So for every idempotent acting on a sheaf, so homology with coefficients in the image of idempotent is the same as the image of the idempotent on homology. Okay? Does it make sense? Из вполне приводимости, но это я повторил доказательство вполне приводимости. Это я повторил доказательство вполне приводимости. Да, ну, чтобы это вывести из... Да, хорошо. Okay, so we have this formula. Now, let's...
So any sheaf with an action of G decomposes uniquely as a direct sum of irreducible.
Yes, so if you have any abelian category with where morphisms are QL vector spaces, and you have an object with an action of G, then it decomposes into direct sum of reducible. Yeah. Mm-hmm. Okay, so this is where I use that my group is finite. That's one place where I use it. Actually, there will be another. So good. So now, so now I claim that this this sheaf H low star QL tensor with V, and so that this sheaf is precisely the local system corresponding to this representation V. So that this is F. And once I have this, the lemma will follow. That's what I want to prove. So, okay, so these are local systems. To see this, let's write this, the corresponding local system. So what is the local system corresponding to this direct image? It's just the sort of the regular representation, if you wish. So this is a this is a cover whose order is order of G, whose degree is order of G. So this is going to be a local system of this rank. And I claim that it corresponds to a representation of, so pi 1 et al. Of C. It maps to pi 1 et al. Of C0 because C maps to C0 and this maps to G. So, so there is a left action of this group on this group algebra where this composition, right? So there is a map from fundamental group to G, and G definitely acts here. So this is a representation of left representation of G of pi 1 of C of the fundamental group. So this is just my V, and now ну, регулярное представление, да, регулярное представление, да, да. So I claim that this local system corresponds to the representation of pi 1 etal of C via the action of pi 1 on this first factor. Now, G acts on this representation by action of G on the right here and by its action on V. The action on V is given to us, right? It's this representation rho, right? So now we are reduced to a result in group theory, so that if I take the regular representation, I tensor it with V, and then take invariance, that's the same as, well, it's the same as home from QL of G to V, right, over G, because this is self-dual, and such homes is the same as V. So this way, we identified this object as a representation of the fundamental group with V itself. Okay? And this completes the proof. Very good. So we realized homology of C with coefficients in a local system as a direct summand in homology of C tilts taken several times. And now we use theory of characters to prove the formula. So let's see. So okay, so I take, so let's take the sum that we want to compute. So this is sum over Q, Q equals 0, 2, of Frobenius traces of the Frobenius acting on homology of our local system. So I will write this as HQ of C tilt with trivial coefficients QL, tensor it with V, and then I take G invariance. Right? This is the right-hand side of the Lefschetz formula, right? What is written here is precisely trace of the Frobenius on this group. That's what you want to compute. Okay? So now, how you compute such a trace? So on this group, on this space, you have action of G on this space, and you have commuting action of F, right? Because on this diagram, you have geometric Frobenius, and you have G. And because action of G comes by base change from a finite field, this G commutes with F. So I want to take, so this space is a representation of group Z generated by this F and this G. And I want to compute the trace of the Frobenius on invariance. So invariance, as we already used once, it's the image of the idempotent given by the sum of all elements of G divided by the order of the group. So I will use this. I will write it as 1 over the order of G times this sum over Q minus 1 to the power Q. And then I have sum over G trace of the Frobenius multiplied by G acting on H Q of C tilde with constant coefficients, right, times the trace of G acting on V. Right? Is it okay? So if I have any representation of the group Z times G, then I can compute, so this is generated by my F upper star. Then I'm using the following fact, that trace of F upper star acting on VG is the same as trace of 1 over order of G traces of F upper star G on W. And this is sum over G. Right? Because so sum of traces is equal to the traces of sum of operators, and this operator is F star acting, well, it's composition of two. It's projection to invariance composed with action of F star on the invariance. Okay? That's what I'm using here. And now, so let's, now we are in position to apply Weyl's formula. So Weyl formula holds for any curve over an algebraically closed field and any endomorphism of this curve, right? So we want to express this trace. Yeah, here I'll also use the fact that the trace of the tensor product is equal of matrices is equal to product of traces. So, so let's compute this using Weyl's formula. So let's see what we'll get. That will be sum 1 over order of G, and it will be so I'm interested in fixed points of this map, right? So let's see. So this G times F acts on this C tilde. G does not act on C. So any point which is fixed under this map projects to a point in C which is fixed under F. So that means that K points of C0. So C0 of K. And now let's see what are the fixed points of C tilde fixed under this map, which Y over X. So this is, that's going to be the sum over all G in G of number of points Y over Y in C tilde over X such that Frobenius of Y is equal to G of X, G of Y, right? there is one correction here. So if I want G act here, I need to put G inverse. Otherwise, I get a right action. I want an action, so I need to put G inverse here. So then points which are fixed under this map are precisely points y such that f of y is equal to g of y. So, and I need to multiply this by the trace, multiply it by the trace.
What do you mean right action? Like f lower star is contravariant function.
Well, so I said that this is a representation of G. How it's a representation of G? I have action of G on C tilde. How does it give me an action homology? If I just look at the induced action, it's not going to be a representation of G. So I need to put G inverse.
So this is like G inverse star.
Yes. So here I have trace of G acting on V. Okay? So what happened here, I just use Lefschetz formula, Weyl's formula, to compute this trace. Good. So now, so the rest of the proof is just a matter of, so we already, you see that we expressed the quantity that we are interested in, namely this one, in terms of sum over rational points of my curve. So we want to show that this guy is precisely the trace of the geometric Frobenius acting on the fiber. This cannot be difficult. It amounts to some finite sets with action of finite groups. So, and let's see why it's what happens here. So let me draw another diagram here. So I have C0, and I have a point, spec K. This is my point X, and I'm looking at the fiber over this point, all geometric points which are lying over X. So here I have C0 tilde, and I can take, so this is a G torsor, and I can restrict this G torsor to spec K. Right? I still have action of G. So this gives me, again, a G torsor on spec K, and this is the same as homomorphism from the fundamental group of this guy to G up to conjugation. So, so I can, if you wish, I can identify by fixing one point lying over X, I can identify this set of all points over lying over X with G itself, right? And then action of the additional information that I will have is so we can sort of identify this C0x K bar with this is a finite set with an action of the geometric Frobenius, and as a finite set with an action of the geometric Frobenius, it's the same as G, right? This has a simple transitive action of G, so I can identify it with G. And the geometric Frobenius will correspond to the arithmetic Frobenius, which is the image of the generator here in the fundamental group, Frobenius corresponding to this point. So, right? So again, explain what's written here. So this is, so I look at this G torsor on spec K, a G torsor on spec K is the same as, a homomorphism from Z hat to G. So I have an element, this Frobenius, which I can think of as an element of G. And so this makes G into, a G kind of a set with a simple transitive action of G on the left and action of the Frobenius on the right. So I will rewrite it. So this is sum 1 over G, sum over X in C0 of K. And now, again, I identify this set of Y with G itself. So this will be sum over G. Now I compute the number of points G prime in G with the following property that so each G prime gives me a point lying over X, and the condition is that the Frobenius applied to this point, which is G prime times the Frobenius inverse, is equal to G times G prime. And times the trace of G acting on V. Okay? Again, so what happened here? So I fix one point lying over X. And then all other points I get correspond just to an element, G prime of my group. Under this identification, the action of the Frobenius is given by this formula. So, this is kind of a double, I can think of this as a double sum over elements of G. So G runs over all elements of G, and G prime runs over all elements. And notice that this condition can be rewritten. This is equivalent to saying that G is conjugate G prime Frobenius X inverse of G inverse, G prime inverse. Okay? So I'm taking sum over all G and G prime with this property, and so traces of G. But the trace of conjugate matrices are the same. So what we'll get is simply 1 over order of G times so look, so this is sum over all G and G prime, but G is determined by G prime. So this is essentially sum over G prime. G prime trace of G prime Frobenius X inverse, G prime inverse, acting on V. Okay? So you see that all these terms are the same because these are conjugate matrices, and what we get is the trace of Frobenius X inverse acting on V, and Frobenius, arithmetic Frobenius is inverse to geometric Frobenius. And this completes the proof. Вот это.
Нет, самое первое.
Самое первое. А просто...
Вейля, непонятно, как трейс G на V вынести за скобку, так сказать. То есть формула Вейля, она для постоянных.
Правильно. Значит, давайте так. Вот это равенство.
Нет, это равенство понятно. Непонятно, как перешли в сумме по точкам.
Нет, но след на V я уже вынес за скобку в этом месте. Смотрите, я сначала считаю след на когомологиях с постоянными коэффициентами, а потом умножаю на след на V. Это произошло раньше. Это отвечает на ваш вопрос?
Сейчас, в каком смысле? Сейчас это вынесло из-за скобку суммы по всем G? Или что ли?
Вот что здесь написано. Значит, вот здесь стоит произведение, стоит сумма по G, вот таких вот произведений. Вот каждый этот след, теперь я применяю формулу Вейля к первому сомножителю.
Вот я не понимаю, что это значит.
Ну что значит? Вот у меня есть многообразие, на котором действует вот такой эндоморфизм. Меня интересует след этого эндоморфизма на когомологиях с постоянными коэффициентами.
Окей, хорошо, то есть просто по коду суммировать.
Да. Okay? So,
Сведения, получается, не пользовались тем, что C3V, а просто если формулу Левшица
абсолютно. Но пользовались мы только тем, что мы не знаем формулу Левшица, но Вейля ее не доказал для произвольного многообразия. Но совершенно правильно. Okay. So, now what will happen now is, so let's try to think how to extend this argument. So we want to prove Lefschetz formula not only for Artin local systems, but for all QL sheaves. So a QL sheaf need not be a local system, but for a curve, this is a kind of a minor problem. So you'll see that that's the main problem is that we have many representations of the fundamental group. We have many local systems which do not factor through a finite quotient. And the argument fails completely. Well, we can't even start because, so we started with a finite et al. Cover C tilde of C, where such that the pullback of our local systems to C tilde is trivial. So if in general there is no such a cover. So what can we do? So the idea is very simple. To first prove formula with finite coefficients, with coefficient in Z mod L and Z. And then any representation, so if V, instead of a QL vector space, a module over Z mod L to the NZ, so it's a finite abelian group, this group is finite, so any homomorphism factors through a finite quotient. Right? So, okay. So what we want to prove is the following theorem, which is a version of the Grothendieck-Lefschetz formula with finite coefficients. So let F0 be now a constructible sheaf of, let's say constructible Z mod L and Z sheaf. on C. Then it gives me its pullback is a sheaf on C, and it comes together with the Weyl structure. With finite coefficients, Weyl sheaves are the same as sheaves on C0, because this Frobenius, it acts through this representation of Z factors through a finite quotient. So the descent, every F with such an isomorphism descends to a sheaf F0 on C0. The corresponding sheaf on C. Then the trace, well, so the sum over Q of traces of the Frobenius acting on homology with compact support of C with coefficients in F is equal to the sum over X in C0 of K of traces of Frobenius acting on the fibers. So that's what we want to prove. Unfortunately, the formulas I stated simply does not make sense. So let's see what's the problem here. So let's look at the left-hand side, right-hand side. So here we have a, what is this? This is a module over this ring with an endomorphism. How are we going to take its trace? So what is a trace? What is a trace of a module over this ring? Suppose it's even finitely generated. Well, we know that it's finitely generated because it's constructible.
Well, maybe we discard something which is torsion of order smaller than L to the n, and then it's just
yeah, so, but unfortunately, then it will not be additive in short exact sequences, and I doubt that this would lead, probably this will. Yeah, so the problem is that if we knew that this is free module over this guy, then of course we will just take a basis, write this Frobenius as a matrix in this basis, and then take the trace. But if it's not free, then what shall we do? Well, the answer is very simple. Take, so I left some space here, take flat Z mod L to the n Z sheaves. So where flat means that the stocks are flat. Precisely, we have now in position to take the trace of the Frobenius on the stocks. But it doesn't solve the problem, because what we are going to do with the right-hand side, the left-hand side. So even if this were a constant sheaf, or well, homology, well, okay, so no, for constant sheaf it's okay. So if this is a local system, then, well, what is H2? H2 is some coinvariance of the fundamental group acting on the fiber, right? This coinvariance is the quotient of the fiber modulo something. So it need not be, even if this is flat, this need not be flat. Okay? So, okay, so my first goal is to make sense of this formula. How would you make sense of that? Well, the idea is the following. So how to make sense of the trace of the Frobenius on cohomology, HQ of C with coefficients in F. Well, the idea is represent HQ by S cohomology of a finite complex of finite free Z mod L to the NZ modules with an action of F. So let's give a name. So let's call this complex R gamma C F. And so this is P dot. So, and define the trace, the alternated sum, -1 to the Q of traces of Frobenius on HQ as alternated sum -1 to the I of traces of F on Pi. Right? So what I'm going to use here is the following fact from linear algebra. If you have a complex, say, of vector spaces with an endomorphism, then you can do two things. You can either take its cohomology and compute the alternated sum on traces on the cohomology, or you can compute just alternated sum of traces on terms. So if I have a complex of free Z mod L to the N Z modules, then well, passing to cohomology and then computing trace need not make sense. But if this expression makes sense. And let's use it as a definition. So this raises a question whether it's possible to represent these groups by as cohomology of some complex of free Z mod to the N Z modules. It's not at all true, for example, that any finite module over this ring admits a finite resolution by free modules, right? For example, if, say, n is 2, then you cannot write for Z mod LZ a finite resolution by free modules. It will be necessarily infinite, right? Because this Z mod LZ has infinite Tor dimension. If you compute Tors of Z mod LZ with Z mod LZ over Z mod L squared Z, you get Tors in all degrees. So it's not a priori clear whether such a representation exists, even if you forget about action of F. And the second question, why it's canonical, why it really does not depend on choices. So it turns out that for cohomology, that in fact it is possible for any flat F, as in the statement. And once this is done, the theorem will make sense. So let me explain how you do this. Okay? So in order to do this, let's make a digression about traces of matrices. So I'm interested in traces, so very end of traces of traces, just traces. Okay, so I will explain this in a slightly more general setting that will be used in the proof of this theorem, not only the statement. So let lambda be a finite ring. So for us, the main example will be like group algebra, something like this, where G is a finite group, right? So I'm interested in lambda modules with an endomorphism. So M left lambda module and F is its endomorphism. So the question is, what is trace of M? Of F? Where does it live? Okay? So let's try to answer this. So to start with, let's make a definition. So let's denote by lambda b mul the zero Hochschild homology of this guy, which is the same as lambda modulo commutator. So this is just an abelian group. So this is abelian group generated by elements A, B, A, B minus B, and A and B are in lambda. Right? So it's not closet under, it's not at all an ideal. So this is just an abelian group. It's not a ring. So, we are going to define traces with values in this quotient, in this zero Hochschild homology. And in order to do this, let's start, well, not for all. It will be defined not for all modules, but for projective modules. So let's start with free modules. Okay. So for a free lambda module, say M lambda n, it's endomorphism. Just matrices. Matrices. M times M matrices with coefficients in lambda. Namely, if I have a matrix A, then what is the corresponding endomorphism? It corresponds to an endomorphism A, which is mapped from here to here, which commutes with left action of lambda, and A of V is equal to VA. I need to use right multiplication because my endomorphism must commute with left action of lambda, right? So there is a bijection between these sets. So now I will define trace map from endomorphism over lambda of lambda so by вопрос? Что-то неверно? Да. Значит, first by identifying it with matrices, then taking the trace of the matrix, and then projecting it to zero homology. Right? That's the trace. The trace is defined to be the composition. Why do I project it? Well, the main property of the trace that we are going to use is the trace of the commutator is 0. So exercise, well, suppose you have two endomorphisms, lambda, say, n goes to lambda, m, and then goes again to lambda. So these are free modules, n. So let's say this is A and this is B. Then trace of AB is equal to trace of BA. And it is here where I need to take this projection. Of course, this trace of a matrix is defined as an element here, but in general, it will not be true that trace of AB is equal to trace of BA. For example, even if these numbers are equal to 1, then, well, then my matrix is just a scalar, right? So AB is not equal to BA in this string lambda. I need to take the quotient model of the commutator. So, but if I do this, then the usual computation with matrices shows that this is true. Right? So this is an endomorphism of, well, one thing is an endomorphism of this guy, another is an endomorphism of this. Its trace is still well defined. Okay. Now, so more generally, so I want to so I want to extend it to endomorphism of free module. Well, so I want to show that endomorphism is well defined, does not depend on the trace does not depend on the choice of a basis. And more generally, I want to show that it can be defined for any projective module. So let P be a finite projective lambda module. So, okay, so, and say F, or phi is its endomorphism. So, what is trace? So, so what is a projective module? So, a projective module is by definition a direct summand of a free module. Well, it's finite, so it's a finite rank. So choose a map, an embedding of P into a free module, lambda m, and this is the projection. So this is A, this is B, such that lambda m is equal to the image of A plus kernel of B, and A, B composed with A is identity on P. So choosing such A and B is equivalent as writing P as a direct summand here. Define trace of phi acting on P is trace of the following. So you take first B, you compose it with phi, and then compose it with A. So what is written here is an endomorphism of this module. And my trace is an element in this ring, in this zero Hochschild homology. Right? So now, the previous exercise, well, another way of putting it, so my P is realized as a direct summand here, so phi is an endomorphism of P. I can extend it to an endomorphism of this free module by letting it be phi on P and 0 on the complement, on the other summand. And then I take the trace of this. And the main property, of course, is that it's well-defined. This is another exercise which follows easily from the previous one. So exercise, trace of phi on P is well-defined. Defined, and its trace of phi composed with psi is trace of psi composed with phi. Right? Okay. So, right. So how does it help? So the zero Hochschild homology is precisely designed, is the kind of target of the trace map from that that assigns to every endomorphism of projective module something. Okay. I'll take 2 more minutes. So now we have addressed, so we can define trace of a projective module, for example, Z mod L to the n Z module. But so homology groups considered separately need not be projective. Well, a finite projective module over Z mod L to the n Z is the same as a free module. That need not be free. Okay, so what can we do? So let's consider the derived category of all lambda modules. So derived category of modules over lambda. So what is it? By definition, so it's the Verdict, well, by definition of the derived category of an abelian category, it's quotient of this is the homotopy category of chain complexes. Well, right now, all. So homotopy category of chain complexes of lambda modules. So what does it mean? So objects here are chain complexes, and morphisms are morphism between chain complexes commuting with the differential up to homotopy. So the derived category is defined to be the quotient of this by the category of acyclic complexes. Acyclic, right? So an important fact in homologic algebra is that if P is bounded, P dot is bounded from above complex of projective modules, then for any complex M, morphisms from P to M and this homotopy category is the same as morphisms from P to M in derived category, right? So what is written here? So first of all, there is a map here, right? So there is a functor from this category to this category. It's not fully faithful. It's not an isomorphism on morphisms in general. But if this guy is projective or free, for example, then morphism from a free module to any complex in the homotopy category is the same as morphism in the derived category. So this is a formal consequence of the following, that if you take, consider a bounded complex, well, this bounded from above complex of projective modules, and take for M an acyclic complex, then this guy is also going to be acyclic. So morphism from a projective complex to an acyclic, any morphism is equal to 0 up to homotopy. That's a formal consequence of this. And you prove it reducing to the case when P is just lambda, where it's obvious. So, okay. So another way, okay, so now I'll make a main definition, right? So let's say definition. So let's define the category of perfect complexes. That's going to be a subcategory in this homotopy category, and it's is the full subcategory formed by finite complexes of finite projective lambda modules. Okay, so now this K perf of lambda, well, it maps to K. It's a full subcategory of K. That K itself maps to the derived category. And by the fact that I mentioned here, this is a fully faithful embedding. Right? Why? Because morphism between finite projective complexes in homotopy category is the same as morphism in derived category. So I can think of this as a subcategory here, right? Well, the usual notation for this will be d perf of lambda. So for any ring lambda, we have a subcategory here, which is just this. It's the image of this fully faithful embedding. These are complexes that can be represented as finite complexes of finite projective modules. So, and I will finish with a definition of the trace. So, main definition. So suppose you have M, which is finite, well, which is perfect. And you have an endomorphism. So endomorphism in derived category. I will define a trace, right? M is P dot in K perf of lambda. Then, so you have phi here. And by this fully faithfulness, it gives me an endomorphism phi of this complex. And I define the trace of phi on M to be the alternated sum, -1, of traces of phi I acting on pi. And this is an element of lambda of the zero-Hochschild-Hamilton. So next time I will start by showing that this is indeed well-defined. It doesn't depend on the, so this phi is defined only up to homotopy, right? So you need to show that homotopy equivalent phis have the same traces and doesn't depend on the choice of this representation. And secondly, we will show that we will kind of characterize this subcategory, full subcategory here, in intrinsic terms in terms of finite third dimension. And we'll show that for any constructible complex of finite z mod L to the n z modules, of flat z mod to the n z modules, its R gamma, which is well defined as an object here, actually lives here. And therefore, the trace of the Frobenius is well defined. And this will make it possible to formulate the Lefschetz formula. And then we'll use a little bit more homological algebra and the same kind of type of argument that we used in this for the case of Artin local systems to prove it, to reduce it to the case of constant coefficients where it's Weyl theorem. Okay. Questions? There is another characterization of this, intrinsic characterization. These are objects such that morphism from this object to any infinite direct sum is infinite direct sum of morphisms. It's like finite dimensional. You can characterize finite dimensional vector spaces among all vector spaces by saying that a morphism linear map from a finite dimensional vector space to infinite direct sum is infinite direct sum of maps. Компактный объект.